Okay, last chapter of the year for my honors kids. Taking a look at what we got today. We're going to start chapter 8. And we're still talking about functions, so we're still in the algebra piece. And this is the 8th grade series, obviously. Again, some of these are showing up for some reason, some of them are not. So I'm actually going to dip right down into 8.1, part 2 question. Have to look at this little video clip. I want to talk a little about these in terms of why they are and why they are not. Okay. So we're talking about, I think we've already got a pretty good feel for a linear function situation. Obviously, anything in the form of that or a variation of the form of this y equal mx plus b represents some sort of linear function. And so you can see that this one, for example, is linear because it would include this and make b 0. Again, the variables that you're using don't really matter. Obviously, this guy right here is in that format. If we take a look at this, if we multiply both sides by 2, we would have 2z equal y. And so in that fashion, it would be very similar to the same look that we'd have in this dude right here. And then if you take a look at the one up above, quite frankly, it's linear as well because it's in this format. The only catch would be we could say, hey, this is the same as y. And in this particular situation, remember, we could move around this idea of 7 minus a by saying, hey, that's b equal negative a, or the opposite of a, plus 7. And so that puts it, again, back into this format of y equal mx plus b, and therefore it is linear. Now, one of the best ways to at least make sure that you understand why these other guys over here on the right side are not linear, let's take a look at, think about what would happen if we graphed them or if we tabled them. So if I took a look at this one and said, hey, y equals the absolute value of x, and I made a table for that guy, and I said, hey, I'm going to let x be, for example, -2, I'm going to let it be 0, I'm going to let it be +2. Take a look at what our answers are going to be here. If I plug in -2 for x, my y value is going to be 2. If I plug in 0, I'm going to get 0. And if I plug in +2, I'm also going to get 2. So from a graph standpoint, if I did that, we're going to get 0, 0. We're going to get -2, comma 2, which puts me about right there. And we're going to get 2, 2, which puts me about right here. So this one actually creates, the absolute value one actually creates a V situation, okay? Move on to my next one, which might be the one that you're a little more familiar with. If I said, hey, that's the formula for area of a square. So if I said, all right, I'm going to plug in S is going to represent my plug-in value, and A is going to represent my output. So again, if I choose to say, all right, I'm going to go, let's just say what, 3, let's go 6, and let's go 9. So if I plug in 3, my area is going to be 9, or my A value is going to be 9. If I plug in 6, my value is going to be, what, 36. And if I plug in 9, my value is going to be 81. So if you plot those as ordered pairs, you know, obviously it's only going to be a quadrant 1 graph because everything's positive. And so if I plot 3, 9, I could also, if I wanted to, pop in 0, 0 here. But if I popped in the rest of them, what you're going to do is you're going to end up with a graph that's going to look like this. Okay? So it's not going to be a linear function. And then as for the last one's really going to get thrown out the window because, again, if you plug in 0 for this x value, plug in 0 for that x value, guess what? You're going to get you know, you can't do it. It's an impossible situation. So even if I go, all right, I'm going to plug in 5, be smart to plug in a multiple of 5. I'm going to plug in 10. I'm going to plug in 15. If you did that, we'd get what? 5. Plug in 5, I'd get 1. Plug in 10, I'd actually get half. Plug in 15, I'd actually get what? 1/3, so on and so forth. And if you plotted those situations, then it's going to be a curved line. Now again, understand, because x is here, they could, I suppose you could argue that they could say x cannot be equal to 0, but you know, the same could be true if I flip that around and said, hey, I'm going to plug in -5, Negative 5 is going to be what? Negative 1. Negative 10, if I plug that in, is going to be negative 1/2. And negative 15, if I plug that in, is going to be negative 1/3. So again, if you want to go ahead and plot those lines, you're not going to get what you think. It certainly is not going to be linear. All right, and I thought that was important to get that point across here. If I take a look at this one, is the function rule linear or nonlinear? So again, based upon what we just went through, we obviously should be looking at this and saying, all right, this one we just said was nonlinear. We said this one was linear because it's in the form of y equal mx plus b, where b would be 0. This one would also be linear. This one would be nonlinear. And this one's in the form of y equal mx plus b, so that one is linear. All right, so if we checked all those out, we should be good to go. Okay, moving on to the third example here. Which equations represent linear functions? And once again, we should say the first one should, because it's in essence y equal half x. The second one does not, because x is on the bottom. And the third one should work because, again, it's in the form of y equal mx plus b, where b would be equal to 0. So our answer should be 1 and 3. Okay? The question, and this is where you got to be a little bit careful by not having enough data. You got a cat who said, hey, negative 1, negative 1, 0, comma 0, and 1, comma 1 are all on the graph y equal x cubed. Therefore, that must mean that this formula, or that this equation, creates a linear graph. And obviously, this is not the case, because if you were actually to graph that using different numbers, this is really the graph that you're going to get. Okay, so you got to be a little bit careful about graphing not enough information. And again, sometimes when we make the numbers that we select tight, we don't see everything that's going on. So that's why I said, you want to spread it out a little bit in terms of the x values and the y values that you pick. Okay, so I don't think there's anything else more from an example perspective that I want to show you. So we're going to jump right into something that we've been doing in this chapter, and that is we're going to go ahead and show you just a few homework questions from this chapter. And again, we would think, since there's only 2 parts there, really part 1 and part there's really the first 2 questions are probably from part 1, the second 2 questions are probably from part 2, and I think we'd be done at that point. So again, which rule describes a linear function for the graph? So if you take a look at the graph that we have over here, and again, we've spent some time already doing this type of thing. First things that we would want to pay attention to is, look, we want to think about being a linear situation. Obviously, you can visually see it's a line. And so we want to find out what, if you recall, the slope is located right here, and that, remember, this represents the y-intercept. I think it's important that you recall those things. So the easiest number to pick is, boom, right there's the y-intercept, and the y-intercept looks like it should be positive 3. So we could slide over here and really scratch out this guy. We could scratch, or at this point, I suppose you could argue we could scratch out everything except for the fact y equal x plus 3. Again, I think I want us to make sure that, hey, are we in agreement that the slope here, remember, if there's no value, no coefficient in front of x, then we're saying the slope is 1. Is the slope 1? Is the rise over run 1? So if I looked at, for example, the x-intercept, and I said, hey, that's up 3 over 3, up 3 over 3, so my slope would be 3 over 3, which in fact is 1, and therefore I feel pretty good about saying that y equals x plus 3. Questions there? We're good to go. And again, the second question is going to play out much the same, so I don't think I need to necessarily get that up with you unless you wanted me to. Oh, you don't? Okay, so we're going to move ahead. All right. Moving on to this scenario, which rule represents a linear function? And in this case, we talked about this one pretty in depth already. We feel as though this one is in essence y equal 1/3 x. We already know that because this is x squared term that one's not going to work, and we already know that because x is on the bottom here, that one should not work. So they're trying to fool us here a little bit. Usually when we see these boxes, there should be more than one answer. And in this case, I do not feel as though there will be. So we hit check answer, and we're good. All right, so look out a little bit for those on some of these 8th grade pieces. All right, that keeps us under, well, 10 and a half minutes, I guess. So I think we should be good to go on 8.1. All right, we're going to go ahead and add 8.2 rate of change in on this. Think rate of change. Another synonym for that would be the slope. We're going to hit up a couple of questions here from part 1. Rate of change of a linear function here. So in this particular situation, all we have to do is pay attention to, hey, let's take that point there and that point here. And what we can see is our difference in vertical. So difference in y over difference in x. That's what we can think about. Remember, that's another name for slope. Recall that in this particular situation, the zip line started at 250 and it went down to 200 in terms of the rise or the run. And that the x value moved from what? It was 0 to 300. Okay, 0 to 300. So if we did it this way, we would come up with 50 over negative 300. And again, one of the big things you're going to miss here is the sign. So make sure that you're paying attention to signs. And so your final answer here should be negative 1/6. Okay, negative 1/6 then represents the rate of change of the linear function in this situation. Okay. All right, moving on to my second example. In this particular situation on the ramp, obviously the ramp, if I move left to right, goes up in a positive direction. So therefore my slope is going to be positive. Once again, we could take a look at these 2 points, if you will, and we're saying, hey, this is what? Negative 4, 0 on my graph. And you could argue then that this is 0, 1. And so one of the things that we could do, if we're talking about the rate of change, you could, for that matter, read the graph and say, hey, I'm going to go up from 0 to 1, and I'm going to go right from negative 4 to 0, so I'm going to go right 4. So you could make the argument that the rise over the run is 1 over 4. You could do it that way. You could use the difference in y over the difference in x if you wanted to. So in this case, the difference in y over the difference in x could be what? 1 minus 0. And on the bottom, it could be 0 minus negative 4, which is 0 plus 4. And so that's how we could get our 1/4. So again, be versatile. Think about different ways that we can come up with these slopes on these particular pictures or videos or what have you. Reminder that if we're talking about the model, the top of the truck, in this case right here, that the slope should be 0 on any horizontal line. Okay, slope is 0 on any horizontal line. And then remember, the slope on this guy is no solution, because if I look at it from a rise over run perspective, there is no run. Okay, and so we'd have 0 on the bottom, and of course we cannot have 0 on the bottom, so that's why it's no solution. All right, so on this particular question, your slope is 0, which should make some sense to you. All right, let's move on to a part 2 question quickly. As we look at a part 2 question, once again, we're talking about rate of change, and the rate of change is the vertical divided by the horizontal. We've talked about this. We've also talked about the idea of making sure that you're paying attention to this formula, y equal mx plus b, which is the linear equation formula. And so in this particular situation, they're identifying with this point and this point, and they said that if we go up 1, 2, 3, 4, 5, 6, and then over 1, 2, 3, then our slope is 2, and then it goes through, and again, this is helpful because it's easy, but it goes through the y-intercept at positive 1. So that's one of the ways, obviously, that we've talked about before, doing it from a graph perspective. Let's take a look at our first example here then. They're going to give us a graph, so I think I'd probably look at this and say, all right, first thing that we should identify with quickly is it's got to be a negative slope, okay? Got to be a negative slope, because as I go left to right, it goes down, so that really only allows us to say, hey, that must be the equation right there then. So the equation is y equal negative 3x plus 3. Again, we could verify this pretty easily. You can see where the y-intercept is, 3. So that would be this piece. And you can see that the slope would be down 1, 2, 3 over 1. 1, 2, 3 over 2. So we're going down 3 and we're going right 1. So easy way to put that together. The rate of change then is going to be negative 3, aka my slope. Okay? Moving on to my equation then on this one, a little bit more difficult. First thing we should identify with is, hey, we're at 0, 0. So if we're at 0, 0, then I'm looking for, this cannot be the answer because I'm looking for it going through the origin. You could plot these points if you choose. You could, I think, a couple different ways you can do it. So you can plot it. You could think of it and say, okay, I got y equal mx plus b. But remember, b is 0, so I could really just erase that. And then plug in the points, okay? And to me, the one that you're going to be plugging in here, you're going to stay with positives if you can. I'm going to plug in 2 for x. So I'm going to plug in 2 right here. And remember, I still have m over there, so 2 times m. And then my y value turns out to be 2/3. And again, I'm just pulling them from that particular spot. So if you would mathematically take care of this, then if you divide both sides by 2, you can do it that way. Or some of us could just look at it and say 2 times what number is 2/3, and obviously that answer would be 1/3. So what we're going to come out of here with is m equal 1/3. That means the slope is 1/3. So we go over here, and obviously that means that my equation has to be that dude right there. So the equation is y equal 1/3 times x, with my rate of change being the 1/3. Okay? All right. Moving on then to my next example. On my next example, they're asking what's the rate of change in this particular linear function. Again, when I say rate of change, you're thinking slope. And so the slope, it should be at this point pretty easy for us to pick. My answer should be 3 halves. Okay, 3 halves, and you can see that is true. So I don't think you have much of an issue on that one. Move on to a part 3 kind of question. Try to keep this under 20 minutes here with 2 sections. I think that would be doing this pretty good. Yeah, I don't like that one. Let's move on. How about this one? So use the values of, for 1 ounce candle and a 5 ounce candle to find the rate of change. So again, if we're talking about, they want us to use this dude and this dude for our rate of change. So I'm going to go ahead and say my difference in y over my difference in x. And I'm going to say I'm at 27.5 minus 5.5, which puts me at 22. And my y value, or my x values change from 5 to 1, which puts me at 4. So you could argue that my rate of change here is what, 5.5. Okay? So they're asking you, what does the rate of change mean in this situation? And so what you should be able to allude to is, looks like for every, what, ounce that it increases, the burn time is 5.5 hours longer. So if you're, the heavier your candle is, so for every ounce heavier your candle is, it's going to burn 5.5 times longer, or for 5.4 more hours. Okay? All right, let me pick up. I think that'll probably do it for you guys. I think you should be able to handle it from there. So I'm going to put the brakes on, and we're ahead of 20 minutes. Have a great day. If you have any questions, please feel free to contact me via email.